Are you able to see the screen now? Are you able to see the screen? Okay. So if you remember in the previous classes, we have learned how to draw the bending moment diagram. Okay. We have learned how to find the coefficients. We have learned how to find the coefficients, how to find the moment. We learned how to find the K value, the Z value, and then AS. Now, I tried to the maximum that I didn't include in test number 1. I didn't include a lot of things which are related to area of reinforcement, since it was the last topic. Anyhow, we stopped after calculating AS, and I told you that we are going to take later on the shear and deflection, which we are going to complete today. Okay, and hopefully we'll start the other topic as well as we are late. Now, when it comes to AS, whatever we have found is something called AS required. Okay, whatever we found previously is whatever we call it as AS required. That is the required reinforcement, or that's the required area of reinforcement based on the bending. So based on the value of M, you see here, AS negative, ASX negative, ASX positive, based on the M value, we calculated the A. So that is the minimum required area of reinforcement to resist the value of bending moment. Are we okay? So whatever we have calculated is the minimum required reinforcement to resist the bending moment. Now, when we choose our reinforcement in reality, whatever we are going to put in reality, we call it as AS provided. How much is required is going to be based on the moment value. How much is going to be provided? How much do I put in reality? It's going to be, of course, something more than the required. Are we clear? Are we clear about the point of required and provided? Required is the amount that you require due to the bending moment value. Provided is going to be something more than the required. You are going to put it in reality. So when you are going to see your drawings later on, whatever layouts, whatever plans that you are seeing, you are not seeing the required values, you are seeing the provided values. Okay. Now, if we see here, we have ASX negative, we have got it to be 241. We have ASX positive, we have got it to be 270. And then ASY negative, we have got it to be 0. Okay, and AS, was it 0? Wait. That's another question. It's this question. Okay, so we have got ASX negative as 315, ASX positive as 238, ASY negative as 230, ASY negative as 227. We said we are going to take the maximum of the two. So 227, and these are the values which are shown here. Okay, so we are showing them here. Okay, we have ASX negative, ASX positive, ASY negative, ASY positive. Now, if you see whatever diameter that we have chosen, we assumed from the beginning, it was a diameter of 10. Okay, it was the diameter that we have chosen was 10 in our problem. Okay, whatever we have assumed from the beginning. So what I need to do, I need to go and search. Now for ASX negative, which is 315, I'm going to go for the line of 10. I'm going to stop at a place where it's going to be more than 315. So we have 314, that's lesser than 315. So I'm going to just cross 262, going to cross to 314. So the other option is going to be 393. Okay, 393, which is more than 315, the required minimum value. So how to write it? We are going to write it as Okay, we are going to write it as T, that is representing the grade of reinforcement. Okay, we are going to write it as T, that is the grade of reinforcement. And then the diameter, so we have 10 as our diameter. And then we have the spacing, which is here. The spacing is 200 millimeter center to center. Are we clear about this point? Are we clear? Okay. Now the same we are going to do for the other three. Okay, the same I'm going to do for the other three. Okay, the same I'm going to do. Same diameter, but now the values are reducing. So what do we have? We have 238, we have 230, and we have 227. So if I go for 10, then the most appropriate answer is going to be 262. So for this one, for these three, one, second, third, we are going to supply T10 at 300 mm center to center. Are we clear?
Mister,
Yes.
I have a question for finding kx minus.
Okay.
Have k is less than or equal to k dash. K dash is 0.156. But how we found k?
You find it using the equation of m divided by FCU square. I have showed you the equations in the last class, right? I have showed you these equations.
Yes.
So using the equation of K. Okay. Any other question?
Sir, if the K is greater than or equal to the K dash, then the compression reinforcement should be required, right? So the AS, we have to find the AS dash?
Yes, but in a slab, I told you, in a slab, the concept of slab, I told you from the beginning, the loading is going to be too small in a specific area. So if you got a doubly reinforced section, if you got a doubly reinforced section in a slab, it means that you have done a calculation mistake. It is very, very rare to have a slab which is doubly reinforced, lesser than 1%. You will not see, I think you will not see even a book discussing a slab which is doubly reinforced. Are we clear? Okay. Now, if you see this table actually is not available in your VS. This table was compiled based on the area of the bars. It was compiled based on the area of the bars. So for example, I used to ask my students now, I want you to use a diameter of 50, for example, or a diameter of 14. What will you do? Now this table will not be present with you all the time. Okay. So how would you do it? Now first, okay, I'm going to teach you how to do it. I'm going first to try to calculate for 10, and then we are going to see. Okay, we are going to calculate for 10, and then we are going to see. Now, okay, now if we have bar diameter of 10 millimeter, okay, a bar of diameter 10, then the area of one bar, is by r square. Okay, so by 5 square. Okay, that's the area of one bar. Okay. Now, if I want to calculate how many bars are there, I should know. Okay, I should know the width of the slab, and I should know the spacing. Now, for example, if I have a slab, we said that this slab is going to cut into a width of 1 meter. We are designing for a width of 1 meter or 1000 mm. If we take 1000 mm strip, that this is 1000 mm now, and the spacing between one bar to another bar, okay, the spacing between two bars is going to be, for example, 200 mm, then you will know how many number of bars. So we can say the number of bars is equal to the distance, that is 1000, divided by the spacing between the bar and the bar. So here in this particular length, we are going to have 5 bars. Are we clear? Are we clear about this concept? Okay. So now our width is something which is fixed, that is 1000. Spacing is going to be the value which is varying. Okay. So for example, if we want to check for 262, for example, how did we get it? I can say that it's by 5 square multiplied by 1000 divided by 300. Okay, where 300 is the spacing. Okay. Now, if we go and have the calculator, we say by. So by is 3.14 multiplied by 5 multiplied by 5. That's 5 square. So this is the area of 1 bar of 10 mm. Okay. This is the area of 1 bar of 10 mm diameter. How to confirm? You go to your extracts. In your extracts, you can see that the area of 1 bar of 78.5 of 1 bar is going to be 78.5. Okay, so we have 78.5. We need to multiply by 1000 divided by 300. So 1000 divided by 300 approximately is going to give you 262. Is it clear how this table is formed? Are we clear now how this table is formed? So if I asked you in the exam, use the diameter of 14, you should not say for me that I don't know how to calculate it because it's not in the table. Are we fine? Okay.
مستر
Yes.
مستر الحين في الدياميتر من 10 نحن عرفنا السبيسنج انه 300 شفنا في التيبل بس الحين في ال 14 كيف بيكون؟
You will assume a spacing and check whether it's lesser than the required or not. Got it? You start from 300. If your area that you are getting is lesser than the required, then it does not fit. Change it to 200. And it goes on. Once again, the area of the bars is equal to the area of 1 bar. So we have a bar of 10 millimeter. So the area of 1 bar is by r square. So by 5 square. In order for me to know the total area, we need to know the number of bars. The area of 1 bar multiplied by the number of bars. How to know the number of bars? The number of bars is going to be equal to the strip that I'm going to take. The strip, which strip? The width. The width is fixed, which is 1000. So I'm taking 1000. Now I should know within this 1000 millimeter how many bars will be there. Now, if I didn't know that it's 200, I'll assume a value. So 1000 divided by 300, for example. Okay. Or for example, in this case, 1000 divided by 200. So I'm assuming a spacing in order to know for me how many number of bars. If you know how many number of bars, multiply it by the area of one bar, you will get the total area of the bars. Now, if your area of the bars is more than the required, then it fits. If it's not, then it does not fit. Where you can see the calculation here, I didn't use a table. You can see that I have used by r square multiplied by the spacing divided by multiplied by 1000 divided by the assumed spacing. So for example, here, how much we have used? Here, how much we have used? If you go and see, here we have used, according to the table, we have used T10 at 200 mm. So T10 at 200 mm, okay, T10 at 200 mm is 393. 393. Now 393 is more than 350. That is okay. It's more than 315. But if I use 225, if I assumed my spacing is 225, instead of using 393, I'm going to use 350. Now 350 is more than 315 as well, but it's more economical than 393. Is it clear? So a good engineer is a person who will pick 393. The engineer who will get the design, or the engineer who will get the project, is going to be the one who is using 350, because eventually he is going to reduce the quantity of reinforcement for the client, and then the client will be happy. What about 449? 449 is having a spacing of 175. Okay, so 1000 divided by 175 multiplied by the area, 1 bar, you will get 449. Are we clear? Always you should be taking something more than the required, but you shouldn't take a value which is very far. Now, if I have 315, both 393 and 350 are correct. But the excellent engineer is a person who will choose something higher than the required, but it's not far. He will be conservative. He will save the reinforcement for the client. Is it clear? Okay, very good. So if the table is not there, you can assume the spacing and find out your reinforcement. And this is what we have. This is what I have done here. You should know, because actually, as I told you, the table is not available in the BS code. You should know the fundamental behind getting the table. Yeah, this is what I say. 350 is closer to 315. So if I'm the one to choose, I'll not depend on the value of the table. I'll depend on this value. This is what I said. Okay, although 225 is not available in the table, so you will not use it. But for me, I use my fundamentals, and I have used 225. Are we okay? Okay, so we'll not spend a lot of time. Now the second step is going to shear. Okay, we are going to go for shear. Now, before going to shear, okay, now returning to that point of spacing. Now when it comes to the spacing, you should have already studied that there is a minimum spacing and a maximum spacing. Minimum spacing, if we have bars close to each other. If we have bars close to each other, we keep putting bars together. Is there any issue? And is there any issue if keeping a bar here and another bar which are very far? Like, can we keep one bar and then another bar at a distance of 1 meter? Can we keep like this? And can we keep a distance between the gravel to be, for example, 10 mm? Okay. Now for each case there is a reason. The reason for case number 1, you are using in your concrete, you are using coarse aggregate and you are using a fine aggregate. Okay. So the typical let's say height of the aggregate is 20 mm. If you remember in your mixed design, you have used 10, 20. You remember this 10, 20, 5 mm gravel? So the maximum size of aggregate that we are using normally is 20 mm. Now 20 mm is the minimum, plus according to the code we need to keep 5 millimeter extra. It means between one bar to another bar you need to have a minimum clear distance of 30. That is 25, sorry. That is 20 mm that you are using, and then the 5 mm which is a flexible gap. Okay. Another thing, now this distance, this spacing is center to center. Okay, so you need to include other than that, you need to include half of the first bar and half of the other bar. That's why in this table they have showed you 50 mm. Okay, now 50 mm is going to avoid the issue of having a problem in minimum spacing. And the same thing, 300 or even 400 is going to go and save you from the issue of having maximum spacing. If you're having maximum spacing, if you're having 1 meter between the bars, cracking is going to happen at the center. Something similar to holding an A4 paper and holding an A0. You will see an A0 is going to deflect because of the distance. Now, in order to avoid the distance, you need to keep an extra support, which is representing a bar here. Okay, so the 50 and the 300 is going to ensure for you that you are not exceeding the maximum and you are not lesser than the minimum. Now, from where that came, once again, if you go to your extracts, it's something that you have studied in the code in your design one as well. Okay, if we go here to the table of contents, we are going to search for minimum crack control. So we have minimum spacing and maximum spacing. So if we go for minimum spacing, okay, if we go to minimum spacing, then it says for you the horizontal distance between bars should not be lesser than h of aggregate plus 5 mm, where h of aggregate is the maximum size of coarse aggregate. Okay, that's 20 in most of reinforced concrete. Okay. And then the maximum spacing, it says for you it's going to be 3D or 750. Okay. 3D or 750. So if we have our D, so 3D or 750, whichever is lesser. Now if we go to our problem, you will see that the D value that we have got, one is 150, another one is 140. So we have 3 multiplied by 140 for the Y and 3 into 150 for the X. So in this scenario, the maximum that you can use is 450. Okay, so the table is going to make sure, or you are going to make sure if you are using that table that you are not going to fall in the problem of maximum spacing and minimum spacing. Is it clear? Are we clear? Okay. Now going for shear. Okay, going for shear. Before we go for shear, how many stresses that you have studied? How many types of stresses that you have studied? How many types of stresses you have studied? Okay, so what are the stresses? So we have shear stress. Okay, shear stress. Okay, other than the shear stress, other than shear stress, have you studied something called axial stress, or whatever we call it as well, normal stress? Have you studied this? Okay. Have you studied whatever we call it as flexural stress? Or whatever we call it as bending stress as well? Have you studied these? Okay, very good. So these you have studied it, I think, in mechanics of materials. Shear stress, axial stresses, and then flexural stresses. Okay. And then there is bearing as well. There is torsional as well. But these are the main things that you are going to deal with. Okay. Now, what is the difference between them? All of them are stresses. Okay? All of them are stresses. What is the equation of axial stress? What is the equation for axial stress? Okay, so axial stress, axial, is going to be force divided by an area, or P over area, as you have said. P over A, or force over area. Okay. Now what about the flexural stress? Flexural stress, shear stress. Okay, now for shear stress, it's V over A. Okay, it's V over A, where V is a shear force. Now flexural stress, you have studied an equation which is my over I. Did you take this equation, which is mi over y? You said BE into Z, that's related to, normally for pre-stress we are using. Have you used my divided by I? Okay, where I is equal to VD cube over 12, and your y is equal to D over 2. So if you have I divided by y, then this is going to be VD cube divided by 12 divided by 2, or divided by D over 2, where this is going to eventually give you VD square over 6, and this is whatever we call it as Z value. And then this can be written. Now if we have I over y to be written as Z, then I can say y over I can be written as 1 over Z. Then this is going to be m multiplied by 1 over Z, and this is going to be m over Z. Yeah. So either to say m over Z, or to say my over I. Are we clear? Are we fine? Okay, very good. Okay. Now, when we talk about the failure, normally, okay, when we talk about the failure, normally we refer to certain things. Like when we talked about the bending, we compared between K and K dash, or whatever we call M and MUC or MCU. Okay? For bending, if you remember. Now, M is representing the moment of the load, and then MUC is representing the moment of concrete, or the capacity of concrete, how much concrete can take. Now, if your moment value or K value is lesser than the concrete capacity, it's weaker than concrete, then no need to have a doubly reinforced section. Okay. If your load is more than, if your M is more than MUC or K is more than K dash, it means that the load intensity is more than the capacity. Okay. So you need to have extra reinforcement in the W. When it comes to shear, once again, we are going to compare between something called V and something called VC, where V is the shear stress for the load, and then VC is shear stress of concrete. Okay. Now, if your shear stress of the load is very small, is smaller than the capacity of the concrete, then you don't require to have reinforcement. Okay. You don't have, or you don't require reinforcement. If your V is more than VC, then at that time you require to have links and shear reinforcement. Are we clear? Are we fine? Okay. Now once again, I'll go to my extracts. Now in my extracts, I'll search for shear. So where is the shear? You can see that shear reinforcement is here. So I'll just click on it. You will see that there are two things. One is whatever we call it shear stress of the load, where it says for you V, which is shear stress, is equal to shear force divided by BD. Okay. So we said, if you remember, we said that V small, which is shear stress, is equal to V divided by area. You remember when we have talked about shear stress? We said shear force divided by area. Okay. So now it has been given here that this is going to equal to V divided by BD. Okay. Now, when we talk normally, if we take a section, okay, taking into account that this is my D capital, and taking this into account that this is, for example, my B value, normally we say the area of the section is equal to P into D capital, or we say that it's equal to B into D small. Which one of them? Do we write it as B into D capital, or we write it as B into D small?
With the D small.
No, I'm not talking about the equation. I'm talking about the area of the section. Leave the equation. Maybe the equation is wrong. I'm talking about the area of the section. The area of the section, is it D small or D capital? The question is very clear. It's D capital, right? Okay. Now we have said, according to our equation, it's shear force divided by the area. So now the question that you need to search for, so you will get more marks in your test number 1. Why in shear stress equation we have used D small and not D capital? Are we okay? Are we fine? Once again, we said shear stress is equal to shear force. Once again, we said shear stress is equal to shear force divided by area. Now the area of the section is B into D capital. Okay, B into D capital. I'm asking you now why the equation of shear stress is not using the D capital, why it's using D small only. Okay, so you have till, let's say you have till 6 o'clock. Those who are having an answer, they can send it for. Okay, till 6 o'clock. Anybody who is having a class after this class? Yeah, the section says B into D capital only. The section says B into D capital, not B into D small. Okay, so let us keep it then till 10 p.m. Okay, can we keep it till 10 p.m. or do you want till the 11:59? 10 p.m. 11:59. 10 p.m. or 11:59. Okay, so 11:59. 11:59. You have till the end of the day. Okay. Till the end of the day. Okay. Now for your attendance, each and every person in the class now, those who are writing 11:59, they will get the attendance of this class. Okay. So you need to write 11:59 in your chat box, so I'll know that you are. Okay. Those who are not writing, they will not consider to be attended. Very good. Okay. Okay. Can we continue our class now? After you have finished your attendance? Okay. So this is the problem that we were trying to solve. This is a problem that we were trying to solve. Okay. Now if you see here, okay, this is my slab. Previously we have drawn, right? If you remember, we have drawn the bending moment for this slab. We have drawn the bending moment for the slab. Now we need to draw the shear force of the shear force of the slab. We need to draw the shear force of the slab. Now once again, how would you draw the shear force? Did I teach you how to draw the shear force? Okay. So the shear force, if you remember, the shear force, we're going to have a line here. And then once again, if we have a support here and a support here, and then we have a UDL, or we have in this way, always when it comes to shear, it's a matter of going up and down. So up, down, and then up, down, and then up, down, and then up. Shear force does not change when it comes to the type of support, whether it's continuous or discontinuous. Is it clear? For bending moment, it will change whether the value is going to be 0 or the value is going to be more than 0. Now, when it comes to shear force, it's a reaction. It's a vertical reaction. So it's going to be there whether it's continuous or non-continuous. Are we clear? Okay. So when we see the shear force, you will see that this is your shear force and that's your other shear force. Okay. So we have two shear forces. Now we need to check. Now the only thing that I need to know that this is the shear force for a discontinuous part. This is the shear force for a continuous part. This is for a continuous part. And this is for a discontinuous part. The values will change. Okay, the values will change between continuous and discontinuous, but the shape is the same. Okay, the shape is the same. It does not change when it comes to the support type. Now, if we go and see, now, do you remember the table? Do you remember the table that we were using for the bending moment? Do you remember the table that we were using for the bending moment? Do you remember? So the big table, okay, the big table, which is two-way restraint. This table, remember this one? There is exactly the same table, but not for the moment. It's going to be for shear force. Okay? There is another table exactly with the same type of cases, but it's going to be for the shear force. How to find that one? We are going to go for, once again, the table of contents. We are going to search for shear. So we go for shear stress of the load, and we are going to see that this is the table. Okay, this is the table. Are we clear? How would you know? Now in this table, it's mentioned to be beta V. V is referring to shear force. Okay, so it's beta V. So we have beta X and we have beta Y as well. It's exactly the same type of table, the same form. The only thing, the values are changing. Okay, so now if we return back to our presentation, we can see that this is two adjacent edges discontinuous. Once again, one short and one long discontinuous. So it's case number 4. Okay, it's case number 4. Now we need to see how much are the values. Once again, for y direction, we have 0.4 and 0.26. So when we talk now, this is the discontinued part. So this beta is going to be now for the y, it's going to be 0.26. And now this is going to be this beta for the continuous part. It's going to be 0.4. Are we clear? Are we clear? Okay. Now the same thing, if you remember whatever we have done in the previous class for the moment, our Ly over Lx is actually 1.25. So we need to take the average between these two. So we have got the average of 1.2 and 1.3. Now what do we have? What do we have? We have 0.485 for the continuous. So for this portion, this beta is going to be now 0.485. And then for the discontinuous, it's going to be this beta is going to be 0.32. Are we clear? There is continuous and discontinuous. There is no positive and negative. Positive and negative only for the moments. Okay. Are we clear till now? So the same steps of whatever we have done for the moment. Only that we are using the other table, which is for shear. Now after that, I have my coefficients. Now if you remember, we said bending moment is equal to coefficient of moment multiplied by W multiplied by Lx square, if you remember. And we said shear is equal to beta multiplied by W or N multiplied by Lx. Do you remember this one? Do you remember these betas? Do you remember the equations that I have given you previously? Okay. So now we have our we have our W value. We already have our Lx value. So Lx is available, N or W is available in all cases. After that, we have our beta. So it's a direct substitution. Okay, it's a direct substitution in the values. Okay. Now among these values, among these values, the maximum value is 36 kilonewton. Now here we need to take only the maximum and we need to check for it. We don't need to go to do the same that we have done for the bending moment, because in bending moment we need to supply the reinforcement. Now for shear force, we are going to check first whether we require or not. Okay, so what we are going to do, we are going to check only the maximum, that is 36. The maximum of the 4 cases is 36 kilonewton. Okay, no need to do for the other values, because they will give you lesser than this value. So now what I have done, this is my V capital. I have an equation which is saying for me that V small is equal to V capital B multiplied by D small. So I know already my V, that is equal to 36. I know my B, that is 1000, which is the width. And I know that we have two D's, one is X and one is Y. Now I need to check the maximum value is for which one. And normally the maximum value is for X only. Okay, so we are going to use dx. So this is what you are saying here, that V small is equal to V capital. V capital is 36. Okay, V capital is 36 in kilonewton. So I have just multiplied it by 1000 to change or to convert it from kilonewton to Newton. So we have 36 multiplied by 1000. V is 1000. dx is 150. And then we have a value of 0.24 Newton per millimeter square as a shear stress of the load. Okay, this is the shear stress of the load. Is it clear? So once again, for shear, what we need to do, we need to find the coefficients. After finding the coefficient, we need to get the shear force. The maximum shear force only is going to be taken to be calculated for the shear stress. Now after finding the V small, we are going to compare it with the concrete. We said if the load is smaller than the concrete, then we need to put shear reinforcement. If this V is more than VC, which is for concrete, at that time you will go for, yes, D is the one calculated earlier. You calculated dx and dy earlier in this problem. Are we okay? Are we fine? Now we have V. I didn't understand you. What do you mean we will look to the higher value? I said for you, among the four values, you are going to pick the highest one. So the highest is 36. Now this 36, is it in the direction of X or Y? It's clearly mentioned here that it's X. So of course I'll be using dx. This shear reinforcement or this shear force will be taken by the reinforcement of X. That's why we need to calculate for dx only. Shear force of Y will be taken by the reinforcement of Y. That's why we need to calculate dy. Based on the assumption, if you are having perfect continuous slab, yes, Amir. If not, then no. For example, if you have a two-way slab and a one-way slab connected together, then no, it's going to be leaning to one side, either left or right. Okay. After calculating V, we are going to calculate VC. Now, from where did we get this particular equation? We got this particular equation from the table here. So this is V small VBD. We are going to go for the second page where it says for you VC is equal to 0.79 divided by gamma m which is the shear stress factor for the material, and then 100 AS divided by BD to the power of 1/3 multiplied by 400 divided by D to the power of 1/4. And once again, you can see here, they didn't use D capital, they have used D small. Okay. Now, if we go here, if we go to our equation, so we have 0.79 divided by gamma, 100 multiplied by AS X provided, because once again we are using Vx. This small v is for X, then this Vs should be calculated for X as well. Okay, so ASX provided, BDX, and then DX once again. Okay, this V small is for X, so we need to compare it with X. We cannot compare X with Y. Okay, that's why in VC now we are choosing everything to be in X, and normally the higher value is going to be in X only, as I told you previously. Okay, now we know our ASX provided. Okay, we know our ASX provided. We know what's your DX value. We know what's our B. The only remaining thing is your gamma. Now we need to know from where to get the gamma. And once again, we'll go for the BS code. Now in your BS code, you will see here, it says for you, allowance has been made in this figure for a gamma M of 1.25. Okay, for 1.25. Are we clear? So the value of gamma M has been given by the code to be 1.25. That is the factor of safety for shear reinforcement. So we have taken 0.79 divided by 1.25 multiplied by 100 into A's provided. Now it depends. If you are using the table, then this value is going to be 393 if you remember. If you are using the way that I have told you, which is area multiplied by the width divided by spacing, I have picked 350. Do you remember? Do you remember this one when we say 390 and 300, 393 and 350? Okay, so it's up to you. Both answers are correct. Whether you are using for your level of studying, both answers are correct, whether it's 393 or 350. Okay, multiplied by 400 divided by 150. So it's a direct substitution. It's a direct substitution here, and we have got the value. We have got the value as 0.497. We have got the value of VC to equal 0.9 or 0.497. Now we need to return back to the code once again, checking if there is anything to be taken into account. Now what the code is saying for us. Now the code is saying for us, first, 100 AS over BD should not be taken as greater than 3. Okay, 100 AS over BD no need for your level of studying, no need to mention. Okay, but it's good to practice it from now. So 100 AS divided by BD should not be taken as greater than 3, and 400 over D should not be taken as lesser than 1. Okay, so now if you go and see, we have 100 AS, so 100 AS divided by BD is 0.233. Now 0.233 is lesser than 3. So that's fine, because it says for you it should not be taken as greater than 3. And then we have 400 over D should not be taken as less than 1. Okay, we should not take 400 over D as lesser than 1. So 400 over D is going to give you 200 or 2.667 to the power of 1 over 4. In that scenario, you are not going to get lesser than 1. Okay, eventually you will not get something lesser than 1. Okay, so you are getting a total value of 0.497, and this is the same. We didn't change anything. It's fitting the criteria. We didn't exceed 3, and we were not lesser than 1. Okay, we were not lesser than 1. The last thing the BS code says for you, it says for you for characteristic strengths.
Excuse me, sir.
Yes.
Sorry for interrupting you, but I wanted to ask about the gamma y, gamma m. From where you get the value of m from codebook?
From here. You can get it from 2 places actually. It's
So
in
it
note.
will be constant for all?
Yes.
Okay, thank you.
Gamma m is a factor of safety which is fixed. So allowance has been made in this figures for a gamma m of 1.25. This is the first place you can get it from, or you can get it from this place as well. In the table of contents, you can go for partial factor of safeties. So we can go here. So it says for you, if you are using the factor of safety for the reinforcement, it's going to be 1.05. For concrete, 1.5. If you remember, we have used these in the Excel. Shear strength without shear reinforcement is 1.25. So you can get it either from here or you can get it from there. Are we okay? It's a fixed value for all the cases. It will never change. Are we clear? Okay. Now it says for you here once again, it says for you for characteristic concrete strengths greater than 25, the values in the table may be multiplied by FCU divided by 25 to the power of 1/3. Okay. It means this table was done for FCU or grade of concrete or C25. Okay, we have done it, or this table was done from the beginning for C25. Now, if you are having something other than C25, then the value that you are getting, it needs to be modified. Okay, so we have got 4.497. Now, this 0.497, when I return back to my problem, I need to check what is the grade of concrete that I have used. So we can see that the grade of concrete that we are saying or we are using is grade 35. Grade 35 is more than 25, so it means that the value that we are using right now needs to be modified. Okay, so once again we have got it as 0.497. The code says for you, if the value of your concrete grade is more than 25, then this value needs to be changed. Why? Because the table and the equation was made only for C25. How to modify it? We need to multiply whatever value that we have got by FCU divided by 25 to the power of 1/3 as the code says. You don't need to check for it, because if there is no requirement for shear reinforcement for X, which is a higher value, then of course there is no requirement to have a shear reinforcement for Y. Now, even if you change taking a dy value, still whatever you will get, you will see that this is going to be the dominant value. If you go here once again, if you're having this particular things, once again your highest value is going to be your X only. Okay, like for example, if we have taken this 29.7, and so we have 29.7 multiplied by 1000 divided by 1000 once again, and then divided by 140. Okay, so it's going to give you 0.22. 0.22 is lesser than 0.24. So eventually X is going to be higher. If X was safe, then each and every other thing is going to be safe as well. Are we okay? Okay. Okay, so we have multiplied because we have a grade more than 25. So we multiplied our VC value, which is 0.497, into 35 by 25 to the power of 1/3, and we have got 0.556. Now, what we are trying to say, the concrete can take a capacity of a shear stress of 0.556 Newton per millimeter square. Any value lesser than 0.556, it means that the concrete can take it without additional reinforcement. Now, the load is causing you a stress of 0.24. Now, do you require to have shear reinforcement, or the concrete is sufficient to have, or sufficient to take this particular stress? Once again, 0.556 refers to that the concrete is able to take a stress of 0.556 by itself without having additional shear reinforcement. Now, if we check, the load is causing me a stress of 0.24. Now, 0.24 is lesser than 0.556, which can be handled by the concrete. So in this scenario, we will say that 0.24 is lesser than VC nu, so no shear reinforcement is required. Okay. So once again, we conclude now. Slabs are going to be singly reinforced. Your K value is going to be lesser than K dash. And once again, always for a shear reinforcement in a slab, it's going to be the case that it's going to be your V is always going to be lesser than VC. So no shear reinforcement is required. If you are getting, to keep it summarized, if you are getting that your V is more than VC, it means that you have done a calculation mistake. Okay, if value to be more than a slab, it means that you have done something wrong with your calculation. In short, yeah. Okay. But for example, in a beam, yes, your V can be more than VC. At that time, you are going to supply shear reinforcement according to case 1, case 2, case 3, whatever you have studied in design of structures. Okay. Now going for the last part of the question, which is deflection. Now once again, if you see what we try to do for bending moment, we said we are going to compare between K and K dash. One is for the load and one is for the concrete. If your K is more than K dash, then it's going to be W. Okay, we said for shear, we are comparing between V, which is for the load, and then we have VC, that is for concrete. Now, if your V is more than VC, at that time we'll have shear reinforcement. Are we okay? Are we okay? Okay. The same thing goes for the deflection. The same thing goes for the deflection. For the deflection, we are going to compare once again between two values. We are going to compare between the actual value of deflection, and we are going to compare between something called a limit of the deflection. Okay, so once again, it's all a comparison. Whether it's K and K dash, whether it's V, VC, and then deflection, actual deflection, and then limiting deflection. How to find it? What we need to do? We need to calculate the actual span by effective depth. Okay, the actual span by effective depth. So we have the actual span by effective depth, our X span is 4000, our dx is 150, so our actual span by effective depth value is equal to 26.67. Are we clear? The actual span by effective depth, or whatever we have done till now, is that the span is 4000, which is x, divided, because we are designing for x, if you remember. And then, of course, if I'm taking x into consideration, it should be x as well. So that's why I used 150, I didn't use 140. Okay, so 4000 divided by 150. It's going to give you 26.67. This is the actual. Now I need to check how much is the limit. How to calculate the limit? Now the limiting span by effective depth ratio is going to equal modification factor into ratio. Now if you remember, we said d small is equal to span multiplied by modification factor into ratio. Okay. Now what do I need to, what I want to calculate? I want to calculate span divided by depth only. So I can bring this one here. So I can say that now span is equal to d multiplied by modification factor multiplied by ratio. For me, I said I want span divided by depth only. Say now span divided by my depth should equal to modification factor into ratio. Are we clear? Are we fine? Okay. So we have actual, and we want to calculate based on the modification factor calculated, not the assumed one, based on the new modification factor that we are going to calculate, and the ratio, we are going to see how much is the limiting span by effective depth. Now, going to calculate, we have two things. One is modification factor, another one is ratio. So we say limiting span by effective depth is equal to modification factor into ratio. Now, if you go and see, this is where we are calculating for deflection. Once again, we'll go to our BS code, table of contents. Now, in table of contents, I'm going to search for deflection. I'm going to search for deflection. So I'll get the equations and tables of deflection. So I'm saying here that there is deflection requirement. So I'm just clicking on it. Now we have ratios. We'll come to it later. And then we have this table where modification factor is there. Okay, where modification factor is there. Okay. So we have, if you can see here, it says for you that we have modification factor. Modification factor is equal to 0.55 plus 477 minus fs divided by 120.9 plus m over bd square. Now we have m value, we have the b value, we have the d square. The only thing missing is the fs value. Now from where we are going to get the fs value? Once again, the code has specified for you the fs value, where fs value is equal to 2 as required divided by 3 as provided, multiplied by 1 divided by beta, where this beta is referring to the redistribution of moments, and we don't have any redistribution, so it's going to be 1. Okay. Now if we go to our equation, we have 2 as required divided by 3 as provided, because we said once again in the modification factor equation there is fs that cannot be calculated, that I don't know the value before calculating it. Okay, before calculating it. Okay. So now we have the fy value. We know what's our fy value, which is 460. We know what's as required, what's AS provided. Okay, that's going to be always for X in the highest value. Okay, now what we can do, 2Fy, that's 2 into 460. The required AS of X, the required AS of X is 315. 315. The provided value that I have used is 350. So my Fs value is going to be 276 Newton per millimeter square. Okay, are we okay till now? Okay, so we have got our Fs. The next step, once again, the next step is to calculate modification factor. I think you have done all of these calculations in your design of structures 1 only. So you have your modification factor. So now modification factor, we need to use Fs, M, which is the highest moment, and then dx. So we are going to calculate it. So 19.6 was the highest moment. We have used the equation, and finally the final answer was appearing for me to come as 1.496. Okay. The modification factor was coming to be 1.496. Now we have got our modification factor. Remaining is going to be ratio. Okay, the remaining is going to be the ratio. Now here I have said that the modification factor is equal, or the span by effective depth is equal to modification factor into ratio. I have used the same modification factor, but now I use another value which was not used previously, which is 23. Okay, now I'll explain this point. We'll end up here and then we'll stop. We'll stop this particular lecture.
Sir,
Yes.
here the effective depth which you use, which is dx, it is correspond the higher shear, which was in the equation of the highest dx. So corresponding to that, we use dx,
No, that's
or we
deflection.
choose the higher between dx and dy.
No, see, the highest deflection will be caused by which moment? The highest deflection will be caused by the biggest moment, right?
Yes.
Okay, once again, we'll return. See here, we have an equation. You have studied that deflection is equal to moment divided by ER. Did you study this one? Have you studied this equation? Where deflection is equal to moment divided by ER? Okay, very good. So whenever the moment is increasing, the deflection is increasing. So for me, the most critical situation is wherever I'm going to check for the highest moment. So the highest moment was for X. That's why I need to use the dx. Is it clear now, Hur? Okay. Now, if you return back to your code, the code says for you, we have 3 cases. We have 7, 20, and 26. Do you remember these cases? So we have 7 for simple, and then we have for a cantilever. For a simple is 20, and then for a cantilever is 7, and then we have for a continuous to be 26. Okay. Okay, so these are the 3 shapes. We have here simple. Here we have cantilever. Here we have continuous. Now for the simple, the ratio is 20. Okay, the ratio is going to be 20. For cantilever, it's 26. I mean, for cantilever, it's 7. And then for a continuous, it's 26. Now that is mainly going to be related to the bending moments. Now, if we see for a cantilever case, okay, for a cantilever case, the bending moment is so high, where we have got the coefficient. If you remember, here we have got the coefficient is 0.5 for a UDL case. Do you remember the coefficient for a cantilever? Okay, which is 0.5. Do you remember? Do you remember the coefficient? Okay. Now for a simply supported with the UDL, you will remember that the coefficient was 0.125. Now for a continuous, will the coefficient be lesser or more? Will the coefficient be lesser or more? Now you can see, actually, if it's simple, it should be like this. But now what has happened? You see this particular line has been shifted up. So this coefficient now is for sure going to be lesser than 0.125. Are we clear? The green is representing the simple case. The blue is representing the continuous case. Is it clear why it's getting lesser? Okay. Now, so we said here, now this is going to go something like this, where this is lesser than 0.125. Now, which of these cases, and let us have another case. Let me just delete this one. I'll just draw it here. We said this is going like this, and then the coefficient here is going to be something lesser than 0.125. And then I have another case where it's like this. Okay, now you will see the bending moment starts with 0. It goes up a little bit in one side only. Okay, it goes in one side only. Now, which one do you think is higher? This case or this case? Is it case number 1 or is it case number 2? Or let's say, rather than saying case number 1, let's say case number 1, 2, 3, and then 4. Now, which one do you think is higher, 2 or 3? Which one is having higher coefficient, 2 or 3? 2. Okay. 2 is having higher coefficient because in 3, certain part of the moment went up. What about 3 and 4? Which one is having higher? Which one is having higher? 3. Okay. So now what I can say, the highest coefficient is going to be for a cantilever. After that for a simple. After that for a continuous one side. After that for a continuous two sides. Do you agree with me? Okay. Now, if we can say that M1, which is representing case number 1, is higher than M2, is higher than M3, is higher than M4, can I say that deflection number 1 is higher than deflection number 2, is higher than deflection number 3, is higher than deflection number 4? Can I say like that? can I relate moment to deflection?
Mister,
Yes.
regarding why we didn't consider the number 2 as the highest compared to the number 1?
Because the coefficient is 0.5 and here it's 0.125.
So it's not depending on the direction if it's under the x-axis or above because of the sign?
No, even though, see, you will be using the coefficient to find the bending moment, right?
Yes.
So the higher the coefficient, whether it's up or down, it's going to give you the highest moment.
Okay, thank you, Mister.
So now we have deflection. We agree. Now what does this mean? It means that this case, which is case number 1, I cannot have a higher span. Do you agree? Do you agree that I cannot go for a higher span in case number 1? Because the deflection is very high. So the smallest span is going to be the cantilever, while the highest span is going to be case number 4, where the deflection is less. Do you agree? Okay. Now to control the deflection, what the code says for us, the code says you need to use a ratio of 7 only. Now, what does 7 mean, and what does 20 mean, and what does 26 mean? If we rearrange the equation, which is span by effective depth equal to modification factor into ratio, or whatever we said previously, that d small is equal to span divided by modification into ratio. Now I can say, by rearranging the equation, that span is equal to d multiplied by modification factor multiplied by ratio. Now if you have kept the ratio to be 7, of course your span is going to be less. So by doing that, you have controlled, or the VS Code has controlled, the deflection of the cantilever. Are we clear? So once again, 20. So 20, and then we have 26. Now I can say that the deflection between case number 2 and case number 4 are not the same, which is in case number 3. So for me, I cannot say number 3 is having a ratio of 20 because the deflection is different. And I cannot say that number 3 is having the same as number 4, which is 26. Because the deflection value, or the bending moment value, is between case number 2 and case number 4. Okay. So that's why normally we recommend using the average of case number 2 and case number 4, whereas it's acting as case number 3. So normally we take the value as 23. From where we got 23, 23 is the average of 20 plus 26. Are we clear? And the question
Sir,
that
also for the one-way slab,
for everything.
if you're having a cases like in one side continuous and another side is discontinuous, so it will be like that. For the one-way slab, it is also drawn in the shorter direction, right?
The concept of deflection is the same whether you are talking about one way or two way. Because actually, if you see, cantilever is only a one-way case. It will never be a two-way case. Okay, so the concept of deflection is the same, whether it's one way or two way. Now, the hint, if you remember the hint behind your question, that question of 2 marks that you were having in your test number 1, was to use this equation, which is span is equal to d into modification factor to ratio, where m over bd square was given to, so you could have got your modification factor directly. Ratio is known by the type of slab. The only thing missing was to find the d value. And if you equate two equations, you will be able to get your d value. Okay. Returning to our presentation, we have used the equation of 1.4 into 23. We have got the limit. So we have a limiting ratio and we have an actual deflection ratio. Which one is higher? So our actual is 26. The limiting or the maximum is to the 34. So we are being safe. The last thing is going to be the detailing. Now, unfortunately, there is no time for the detailing now. I'll explain it in the upcoming class. For example number 2, you need to go through it. I'll explain only one thing, which is like making the confusion here, that how to solve for a slab which is half continuous and half discontinuous. Only that part. The other parts I'll not go through them, but the full solution is available. How to choose the cover and everything. Everything is available in the PowerPoint itself. Okay. So if you have any question regarding example number 2, prepare it for the upcoming class. I'll highlight it directly, but I'll not go and solve the full of example number 2. We are already late. Any question for today's session?
Mister,
Yes.
the modification factor, you assume it's 1.4.